Hello friends, this video on p block elements part 8 is brought to you by examfear.com. No more fear from exam. So these were the similarities between the boron and silicon. So if you see, this is nothing but the continuation of diagonal relationships. If you want to learn more about this diagonal relationship, please watch the previous videos. And as far as similarity between the boron and silicon is concerned, these are the list. So let's talk about the group 13 elements now. We have talked about the p block elements, the overview of p block elements, the inert pair effect, the diagonal relationship, the trends in the p block elements. Let's talk about the boron family now. We will talk about two family in this chapter, the boron family and the carbon family. Let's talk about the boron family now. So let's talk about boron. Boron is a rare non-metal. Please note this first, it is a non-metal and is a little rare. It's not that very common. It generally occurs as orthoboric acid and borax and carmine. So formula for orthoboric acid will be H3BO3. We'll study more of this in the next few slides. Borax is also, we'll study more of borax, will Na2B4O7.10H2O, and carmine will be Na2B4O7. Instead of 10 it will be 4H2. So these are the various compounds of borons where it exists: orthoboric acid or boric acid, borax and carmine. And there are two isotopic form of boron, 10 boron and 11 boron. So this 11 one is 81% and the 10 is 19%. And the aluminium is the next element of the this boron is done. The next is the aluminium. Aluminium is the third most abundant element in the earth crust. So it is pretty much available and it is 8.3% by mass. You see a lot of utensils you must have seen in the home which is of aluminium, and it's pretty exhaustively used in industry also, right? And boron is something, it looks like this. There are two forms of boron, crystalline and anhydrous. We'll talk about that. This is the crystalline form of boron. We'll also give you a picture of anhydrous form of boron. This is aluminium now. And for aluminium, the bauxites and the cryolites are the minerals of aluminium. So the bauxite formula is nothing but Al2O3 2H2O. This is my bauxite. And I talk about cryolite, it is Na3AlF6. This is the formula of cryolite. The next is gallium, indium and thallium, and they are less abundant in nature. These are my gallium, indium and thallium. They are less abundant in nature. You see the thallium is so reactive that it is kept in this sealed container, right? So this, you see the gallium also is a little metallic luster, and indium also is looks like metal only. These are my elements of the group 13 element. This is how they look. This is my boron, aluminium, this is my gallium, this is my indium, and this is my thallium. Let's talk about the group 13 elements, the boron family, the trends. The trends will talk about the electronic configurations of the boron family. We'll talk about the density, we'll talk about the melting and boiling point, we'll talk about the atomic and ionic radii, we'll talk about the ionization enthalpy, we'll talk about electronegativity, we'll talk about the metallic character, we'll talk about the oxidizing and reducing agents, we'll talk about the oxidation states, we'll talk about the nature of compounds, and we'll also talk about chemical properties. So we'll talk about all these trends for the boron family now. Let's start with the electronic configuration. So the electronic configuration of the boron family is Ns2Np1. So if you see, for boron it is helium 2s2p1. So it is in this format, Ns2Np1. For aluminium it is neon 3s2 3p1. So if you see, Ns2Np1. This is for aluminium. For gallium, if you see, 3d10 4s2 4p1. Correct? So if you see, 4s2 4p1. Correct? This is gallium. For indium also, if you see, 5s2 5p1. For thallium also you see 6s2 6p1. So if you see, it has this trend of Ns2Np1. Let's talk about the density now. So density is what? Density is, so as we go down, the density. So if you see, the density of boron is 2.35. It has increased. Aluminium, gallium, all the more increased. Indium all the more increased 7.31, and thallium is 11.85 all the more increased. So as you go down, the density increased. Why? Because the mass increased a lot. If you compare boron, the mass was, atomic mass was almost 10 actually, just double it. For element was 26, 62, this is 98. So really the mass is increasing vigorously, and volume is also increasing, but not that much, right? So the mass by volume is increasing, so the density is also increasing as we go down the. Let's talk about the melting and boiling point. So melting and boiling point depends on what? The melting and boiling point depend on the structure actually. See, if we talk about carbon example, I'll just give you example. Carbon has 3 allotropes now. Graphite, let's only talk about 2 allotropes now, which we know, graphite and diamond. Both have same carbon, right? But depending on the structure, one allotrope of carbon, that is diamond, is very hard. The other is graphite is soft. The coal is soft, right? So the melting and boiling point depends a lot on the structure. And obviously, not only the structure, the force of attraction also, right? The bond strength actually, bond strength. Example, I have 2 chemicals X and Y element, they're bonded, the bond strength also matters, right? So it depends on the structure and the bond strength. The bond strength, for bond strength we have the, we will consider the atomic size only. The moment you go down the groove, the size of atom increase, right? The size increase, so the bond is not that strong. If you see, the smaller size atoms make a weak, stronger bond. So I'll say size is indirectly proportional to bond strength. Actually, this you will see everywhere. So if I have 2 small atoms, they're forming a bond, and one small, one big. If you see, this bond will be bigger, strong strength. The bond of this A compound will be stronger than B, because in B if I have one strong big and one small. Even 2 big and 2 small, if you see, this is C and this is D, let's suppose, this guy is more stronger than C. D is more stronger than C, because smaller the atoms, the greater is the bond. That's the tendency we have seen. It depends on 2 things. So the first thing is, if you go down, the size increase, so that the bond strength will decrease, right? So bond strength decrease, so that the melting and boiling point will decrease. Obviously, the bond strength is weak, it will easily melt and boil. So if you see, the trend is pretty obvious, right? It decreases actually generally. But there are some different in trend. The trend is not very clear. Why? Because it also depends on the structure. So if you see now, the boron has a pretty high boiling and melting point. Why? Because of the structure. You see, the boron structure is something like this, right? So since the boron structure is something like this, it has high melting and boiling point. So this is because the structure is called isohedral structure. So this structure is isohedral structure, and because of this, the melting and boiling point of boron is very high. This is for boron. But if you see here, for gallium, it is very less. Why? Structure. So you see, the gallium exists as this form, right? Ga2. Or if you see the compounds of gallium trichloride, just like this, independently, they don't have this complex structure. And so they have low melting and boiling point. Correct? Hope you understand. You'll keep this in mind. The moment you talk about melting and boiling point, you have to talk about, it's all about the bond, right? So if the structure is very complex, it is very difficult to break. And also if this bond is very strong, difficult to break, right? So there are 2 things that defines actually the melting and boiling point. The first is the bond strength, how strong or weak the bond is, and that also depends on a lot of factors, right? The size of the atom and all, right? If you have big size, the strength is less. If you have more small size, the strength is right here. If you have small size, the strength is more. So just understand these 2. Holding 2 different groups together. 2 different groups, let's suppose they are class 1 and class 11 and class 2, class 12. Holding these 2 groups together is difficult, but holding 2 different students, let's suppose there is student 1 and student 2 from 2 different class, that is pretty easy, because you don't need that much energy to hold 2 different students, right? Because they'll have same band and they can easily become friends and they can maintain relationship. But if you want to maintain 2 different class and want to maintain Relationship between two different classes is difficult because there's so many people, right? And not very easy to maintain the bandwidth and all. So the bond strength is less between two different classes, but if you talk about two different people, the bond strength can be good actually. Similarly here also, if you see, if you're small size, the bond strength is more. High melting point, big size, the bond strength is less. Also it all depends on the structure, how complex structure it is, right? It's a very complex structure, it's difficult to break. Same thing if you see in the case of diamond, the structure is very complex. It's carbon, still a carbon. If you compare carbon and coal, coal and diamond both have the same component, it's carbon, but one is very hard, one is very soft. Structure also matters. So let's talk about the atomic and ionic radius. You can just see in this fashion, the atomic and ionic radius. This is my covalent radius actually, and this is my atomic radius as per Slater. So here if you see, the covalent radius is following the pretty good trend as we have discussed. The moment you go down the group, the shells increase, so the size increase, the charge also increase, but they have poor shielding effect, so the atomic size increase. Let's talk about this exception now, right? So we have seen the aluminum and gallium. Aluminum is bigger than gallium. We have discussed this actually. When you see aluminum and gallium, you write the electronic configuration of aluminum. It is neon 3s2 3p1. Talk about gallium, it is argon 3d10 4s2 4p1. So here if you see 3d orbitals come into picture, and 3d orbitals have poor shielding effect, thus the gallium electrons has more effective nuclear charge. So actually the gallium is smaller than, right? This is smaller than aluminum because of the poor shielding effect by 3d orbitals. This is only for the atomic radius, but if you see the covalent radius, it follows a general trend. Let's talk about the ionization enthalpy. So we have discussed this also. Ionization enthalpy is nothing but the energy required to pull one electron, energy required to pluck, actually I say pluck electron. So we have different ionization enthalpy. So you can see this is the first ionization enthalpy, the energy required to pull one electron. The second ionization enthalpy, the energy required to pull second electron. And then we have something called third ionization enthalpy, that's the energy required to pull third electron. These varies depending on the situation, right? Because sometimes just by giving one electron, example in case of sodium, you will give one electron, it will become stable. So first ionization enthalpy is less, but the second ionization enthalpy will be very less. Why? Very more, because sodium is already stable with Na plus, and it won't give more electron, right? So to take out one more electron, it will be difficult. So it needs more energy. So example we see for calcium, the first and second is also comparable because it will easily give second also. For boron also, if you see, energy required to give take one electron, first electron is 801, second is 2427, third is almost same because it easily gives third electron to become stable. Don't see much difference here, right? So that's all about the ionization enthalpy. And if you see the trends, if you go down the group, what happens is the ionization enthalpy increases. Sorry, it should decrease. Why? Because the size is decreasing, increasing. Size is increasing. So it's easy to pluck one electron from here as compared to boron, right? Easy to pluck electron. Here it is difficult to pluck electron, and it is very easy to pluck. Correct? So if you see, this is difficult to pluck electron, easy to pluck, very difficult to pluck, very easy to pluck electron. So if you go down, the ionization enthalpy is decreasing because the less energy is required to pluck electron. Here also we'll see a little weird thing here. Gallium, it is more than aluminum. Why? Because gallium size is less. We have discussed this. Since the gallium size is less as compared to aluminum, so it is little difficult in case of gallium. For example, if you see gallium and aluminum, aluminum is bigger than gallium, right? So the atomic size, so if you see, it is little difficult to electron as compared to aluminum, right? So since little difficult to pluck electron as compared to aluminum, so it has more ionization enthalpy as compared to aluminum. Let's talk about the electronegativity now. So electronegativity is what? Tendency to attract or pull shared pair of electrons. This depends on what? Size and desire, right? The capability and desire. So as far as desire is concerned, the desire is all same because the outermost electron has same electron in a particular group. So we'll not talk about desire part here because each of the elements we have in this boron family has similar desire, but as far as the capability, the size is concerned or effective nuclear charge is concerned, it varies. So if you go down the group, the size increase, size is inversely proportional to the capability, right, to attract electron. Hope you understand this. So the size is increasing, the capability to attract electron decrease, and thus if you see, if you go down, the electronegativity decrease. But there is again a variation here. Gallium and aluminium, the same thing. Aluminium is bigger than gallium. This is aluminium and this is gallium. Since aluminium is bigger than gallium, right, we see that in case of aluminium, gallium has more capability to attract electron as compared to gallium because gallium is size less. So gallium has less more electronegativity than aluminium. Let's talk about the metallic character. So if you see the metallic character, my boron is what? Boron is metalloid, and these are my. So if you see the metallic character is increase as we go down the group, right? The metallic character increase. Why? Because metallic character is what? The tendency to lose electron, right? So if you go down the group, the size increase and these electrons can easily be lost. So tendency to losing electron increase. Since the tendency to lose electron increase, the metallic character also increased. The reducing properties. Please pay attention here. This is a little tricky slide. So reducing property means what? Tendency to get oxidized, right? So that is tendency of aluminium to becomes Al3 plus, boron to becomes B3 plus, right? We're talking this tendency. Gallium to becomes Ga3 plus, iron to becomes iron3 plus, and so on, right? Thallium to become thallium 3 plus. This is what we are looking for. This is the tendency we are looking for in reducing properties. So typically as we go down the group, as we have seen, the metallic character is increasing, so the reducing property should increase, correct? As we go down the group, the tendency to the metallic property is increasing, right? So it should increase all the more, typically going by that logic. But there is a catch here actually. If you compare the boron and ammonium, yes, true. But if you compare aluminium, gallium, indium and thallium, it does other way around. Why? Because of inert pair effect. So because of inert pair effect, as I told that, the moment you go down the group, since the size is increasing, the s orbitals don't take part in the reaction. So what happens is, thallium instead of giving +3, it has more tendency to give +1. Similarly, indium also has more tendency to give +1. Gallium also has both +3 and +1 oxidation state. But these guys are predominantly +1. You see, this guy is +3, this is also +3, this guy is +3, +1, and these guys are predominantly +1 only. So if you see, this is decreasing, right? Tendency to become oxidized itself is decreasing because of inert pair effect. If you just see the size increasing, atomic size, then you will get to a wrong answer. You have to see the other part also, that is the inert pair effect. So because of inert pair effect, if you see, if you talk about the reducing property of starting from aluminium, aluminium has more reducing property than gallium, then indium, then thallium. And this is because of inert pair effect. Hope you understand this. Typically it should increase going down the group, but because of inert pair effect, this is other way around. Let's talk about the oxidation states now. So typically group 13 has oxidation states of +3, and as we go down, the +1 becomes more prominent. That's what if you see, it has +3 and +1 because of inert pair effect, and as you go down, the +1 is more stable due to inert pair effect, and that's why we have the reducing property has that trend. And we have seen that why, because of inert pair effect, my s orbitals don't take part, right? So we have 3 minus 2, that is +1 is the oxidation state. So I have 3 and +1. This guy is typically +3, this guy is also +3 and +1. These guys are also +3 and +1, the +1 more dominant, and this guy is mostly +1 and +1. Let's talk about the nature of compound. So if you see, the boron is very small in size, right? Since boron is small in size, it cannot lose 3 electrons. See, to be stable, since it has 3 electrons, 3 extra electrons, in total it has 5 electrons altogether, it cannot lose 3 electrons, right? Or it cannot give 3 electrons to another element, so it generally shares the electron. So only covalent is seen here, only covalent compounds are seen here. Hope you understand it. See, for example, in sodium, it has 2, 8, 1, 11 electrons. It can easily give 1 electrons and it can form ionic compound, right? But in case of boron, it can't give 3 electrons, because the moment, for example, in calcium also, right? Calcium has 2 extra electrons. It can give 2 electrons. Or let's take magnesium. Magnesium is 282. This is sodium. This is magnesium. Magnesium can also give 2 electrons, right? It is pretty okay for him to give 2 electrons. But for boron has extra 3 electrons. Correct. And total electron is 5. It's very small in size, so it cannot give. See, I have only 5 rupees, I can't give 3 rupees, right? It's good that I will become stable by having 2 rupees, but I can't give more than 50% of my money I have. Correct? So it won't give 3 electrons. So what it will do, it will share electrons with others and it will form covalent bonds. Correct? Please note here, why it cannot lose 3 electrons, because it's very small in size, first thing, and it has to lose almost 50% of the electrons. It has more than 50%, which it won't want to. So it always forms covalent bond. It's a very critical concept. Boron always forms covalent compound. Now when we talk about aluminium, it is 13 here, right? So it is 2, 8, 2, 3. So the P has extra, 2, 8, 3. So it has 3 valence electrons extra. Correct? So it can easily give 3 electrons to form a bond. Also it can share also, because there is no harm in sharing, right? It's all the compounds are little mean. They want to take electron also, they want to be stable also. So sharing and becoming stable is a better option. So it forms both covalent and, if required, ionic also. So it forms both covalent and ionic. And these guys, they form ionic compounds. So if you see, as you go down, the tendency to form ionic compound formation tendency increase. So hope you understand this. Boron always form covalent compound, small size, cannot give more than 50% of the electron it has. So it shares the electron, form covalent bond. Aluminium sometimes shares, sometimes gives the electron, so it forms covalent and ionic bond almost. And these guys form ionic compound as well. But aluminium, which mostly form covalent, but it forms ionic sometimes. And if you go down, the ionic character increase. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.